We can start with the first talk now with Eugene Ferapontov. Very happy to have him here, and he's going to tell us about the functional reductions of the kinetic equation for soliton gas.
Thank you, Vincent. It's a great pleasure to thank the organizers for giving me a chance to speak in front of the audience of experts. So this will be a report on joint work with Maxim Pavlov and Pierre-André Vergallo, who is here. So this is the plan. I will start by introducing the kinetic equation for soliton gas that we have all seen in the previous talk. Then I will discuss delta functional reductions, also known as cold gas reductions of the kinetic equation, and discuss some of their properties, such as linear degeneracy, general solution, and Hamiltonian aspects. Many of these aspects generalize to the full kinetic equation. And in particular, we'll discuss the hard rod case, where we have linearization and Hamiltonian formulation for the full kinetic equation. Can you hear me? The back, yeah? And the talk is based on these two papers with Maxim Pavlov, where we discussed integrability of cold gas reductions, and with Pierre-André Vergallo, where we constructed Hamiltonian formulation for these reductions. This is the kinetic equation for soliton gas. I come from a different community, so my reference goes to Gennadiel, who derived this equation in 2003, and then in full generality, they wrote this equation with Anatoly Kamchatnov in 2005. So this is a system of, it's an integro-differential system for two functions, f, which is a function of eta xt, and s, which is also a function of eta xt. All right, and there are two capital functions. Capital S of eta is just a given function. It doesn't depend on x and t. It's called the free soliton velocity. And g of mu eta, which is also independent of x and t, is called the two-soliton interaction kernel. So to define the system, I need to specify two functions, and then the system is fully defined. Let me maybe show you. So there are different types of soliton gas depending on the choice of these two arbitrary functions. Let me show you classical examples. For instance, KdV soliton gas, S of eta is 4 eta squared, G of mu eta, two soliton phase shift is this. Shine-Gordon, hard rod is the easiest one, where S of eta is eta, and G, the phase shift, is just minus A, as discussed by Benjamin in his talk. And there are also further examples, quite interesting kernels, G of mu eta. And I will say a few words. My original reason for looking at this was, okay, I thought, we will take this delta functional reduction, this hard rod, cold gas reduction, and apply any of the known integrability tests. And this will give us constraints for S of eta and G of mu eta. Probably I'll get a kind of functional equation for the two-soliton kernel, and I'll get all these nice functions by solving. Unfortunately, it hasn't happened, and we proved with Maxim Pavlov that this cold gas reduction is integrable for any functions, S of eta and G of mu eta, just any. You don't even need to assume symmetry of this kernel, right? Just any functions. Okay, my current understanding is that the full kinetic equation should be integrable for any choice of these arbitrary functions. Right, but then we kind of modified our problem a little bit. We asked, let's classify those S of eta and G of mu eta for which the cold gas reduction is locally Hamiltonian. I will explain everything in detail. And this imposed a constraint for the kernel, namely the kernel must be of this form. So some function of mu times some function of eta times some function of the difference. So in fact, there are three arbitrary functions in this ansatz. Right? You can check that all these cases fit into this class, right? All of them of this type. And the theorem is that whole gas reductions are locally Hamiltonian if and only this property holds. Right? Okay, let me move on to this whole gas reductions. These are reductions of this form, where the function f of eta, x, and t is the sum, it's a kind of delta functional ansatz, where ui of xt and eta I of xt are functions to be determined. Right, so if we substitute this ansatz into the kinetic equation, you get a quasi-linear system for ui's and eta's. So uit equals this, eta it is this, where I need to explain what are vi's. So ui's and eta's are just these values, right? These entries. So vi's can be recovered from this linear system, right? We have this linear system, and this is a linear. This system is just ordinary linear system for v's. You solve it, and then you substitute them here, and you get a system written in terms of u's and eta's only. Right here, I use epsilon ki is the two soliton kernel evaluated at eta k, eta I, right? So this system has nice properties. First of all, the matrix of this system consists of n Jordan blocks of size 2 by 2. I actually prepared here something that is not on my slides. Let me show you this. Oops. So let's look at, so here I wrote a general quasi-linear system. In indices, it looks like this, right? Indices run from 1 to n. Over the repeated index, there is summation, right? There are, suppose that the so-called Heintius tensor of this system vanishes. So Heintius tensor for a 1-1 tensor, like VRG, is the same as curvature tensor for a metric. If the curvature tensor of a metric is 0, then the metric can be reduced to constant coefficients. If the Heintius tensor of a matrix is 0, then it can be reduced. I'm not writing here this expression for the Heintius tensor. It's kind of an analog of the curvature tensor. Then the system can be reduced to a canonical form depending on the Jordan structure of the matrix VIG. For instance, suppose that the matrix V and my matrix is semi-simple. It means all its pointwise, all its eigenvalues are distinct, real and distinct. Then it can be reduced to diagonal form by change of variables. This was also discussed by Benjamin, right? By change of variables. Here I showed just 4 by 4 case. So you can reduce your system, your matrix to diagonal form, where all these fields, they depend on all R's, so the system is not decoupled, it's coupled, because V's depend on all R's. So if the pointwise structure of the matrix V is one single Jordan block, then you can reduce and the Heintius tensor is here. That you can reduce your system to this kind of chocolate, upper triangular chocolate style. You have V1 on the diagonal, it's a unique eigenvalue. Jordan block has only one eigenvalue. Then above is one and the same entry, V2, then V3, V4. It's kind of constant along these diagonals. So in general, suppose that my matrix V is so-called gel regular. It means that it has Jordan blocks, but different Jordan blocks have different eigenvalues, right? It's called gel regular. And the Heintius tensor is 0. In fact, Heintius tensor is 0 for all Whitham equations. It's a very natural equation, right? So then the matrix can be reduced to a canonical form, which consists of Jordan blocks of this type, chocolate type. In particular, this soliton gas system, this one, it can be reduced to 2 by 2 Jordan blocks of chocolate style. it's n 2 by 2 blocks. So V1, 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 V2, 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 and so on. So 10 Jordan blocks of size 2 by 2, right? Yeah, but this happens in this reduction happens in special coordinates, not in these coordinates UI eta. You need to change coordinates. Then the system becomes this. And now I will show you how to change coordinates. Right? So, first of all, as I said, this system, quasi-linear system, consists of n 2 by 2 Jordan blocks. It is linearly degenerate. I will define this later. It's hydrodynamically integrable. This means it possesses infinitely many hydrodynamic type conservation laws and commuting flows, depending on the necessary number of arbitrary functions. In fact, I will show you, instead of writing all these conservation laws and commuting flows, which become messy as n grows, I will write its general solution. And its general solution is quite simple and works for any n, right? And then it turns out that this system possesses local Hamiltonian formulation for this special kernel that I characterized on the previous slide. All right. So now how to reduce the system to n Jordan blocks of size 2 by 2. And the system takes this form, which is precisely, this form is precisely this Jordan, this is the collection of n Jordan blocks of size 2 by 2. By the way, let me maybe make a comment. Ken asked a question if the system, the full system is diagonalizable. In fact, these delta functional reductions are already not diagonalizable. For instance, this eta i's can be called Riemann invariants, but there are also additional variables ri's, which are not Riemann invariants. So this system has some Jordan part. It's not fully diagonalizable, in my opinion, right? At least for delta functional reductions, it certainly is not diagonalizable. So in these variables ri, eta I, where ri's are defined by this formula, we have these equations. So n 2 by 2 Jordan blocks, and I need to specify these coefficients vi's and pi's as functions of r's and eta. Yeah, r's and etas. And okay, there are explicit formulas. It's done as follows. I will not use them, but anyway. So let's introduce n-pi matrix epsilon hat with diagonal entries R1, Rn, and off-diagonal entries G of eta I, eta k. So it's a matrix depending on r's and etas. R's on the diagonal and eta ij of diagonal entries, right? Then I introduce its inverse. Okay, it's convenient to use it with the minus inverse of this matrix epsilon. I call it beta. So for 2 by 2 case, I have this matrix epsilon and its inverse, right? And then all these variables vi's and pi's are expressed in terms of the matrix elements of this beta hat by this explicit formula, right? I'm not stopping on them. Yes, it's impossible to memorize them anyway. So there are explicit formulas for vi's and pi's in terms of r's and etas.
G is always invertible.
Huh?
G is invertible.
Yeah. Now linear degeneracy. I said that the system is linearly degenerate. What does it mean for systems of Jordan block type? So first of all, a general quasi-linear system of this form, right? General is said to be linearly degenerate if eigenvalues of the matrix Vij are constant in the direction of the corresponding eigenvalues. So derivatives of eigenvalues in direction of the corresponding eigenvectors, I see, right? For diagonalizable systems of this form, so there is no summation here. For systems in Riemann invariants, right? Linear degeneracy means that VI, ith characteristic speed, doesn't depend on its own Riemann invariant. All right, so this holds. For systems of Jordan block type, namely systems of this type as soliton gas. Here I copied the system for soliton gas. Right? Linear degeneracy means that eigenvalues do not depend on Ri's. Vi doesn't depend on R. dvi by dri equals 0. Right? First of all, this property holds for delta functional reduction, so the soliton gas. And in general, linear degeneracy prevents a breaking of initial data. So it's known to lead to global existence results. At least this is true for delta functional reductions, and probably Benjamin would know this much better than me. Probably it's true that the full kinetic equation has global existence results. Is this true? Yes. Okay. Right. Now, general solution. It turns out that the system with I explained how to calculate VIs and PIs in terms of R and beta. So this system possesses a general solution, right? Implicit, not explicit, implicit solution. So it's given by this formula. So I need to explain, first of all, mu I of theta I are just n arbitrary functions. Now, what are phi i's? Phi i's are functions of all etas, and they satisfy this system of equations. Each epsilon ij are interaction kernels, the soliton interaction kernels evaluated at eta j, and mu j are these arbitrary functions, and phi I differentiated by eta j is this, right? So this system is integrable in quadratures. Yeah, you need a quadrature to solve for phi's, right? Consistency conditions are satisfied. So once you recovered phi's from these equations, you put them here. From these n equations, you express etas as functions of x and t. These are like analogs of hodograph equations, right? But for systems of Jordan block type. So you express etas as functions of x and t from these. And then from the first set of equations, you just get Ri's explicitly, right? Explicitly. Once you know etas, you define R's, right? Explicitly. This is a general solution. You see, n arbitrary functions come from this mu I of eta I, and extra n arbitrary functions come from phi i's. Because you see, for phi I, we have j derivatives, where j is not equal to I. So another arbitrary function comes from phi I. So we have two n arbitrary functions, and this is the general freedom for solutions of this two n components system. All right?
So what if the function is 0?
Sorry?
What if the function is 0?
Which?
Mu I.
No.
Or do is 0?
Yeah, here, yeah, okay, non-zero. Non-zero. So I also claim that this system is hydrodynamically integrable. It means that it possesses infinitely many conservation laws and commuting laws depending on the right number on two n arbitrary functions of one variable, right? And they can be written out explicitly. The problem is, as n grows, the formulas for commuting flows and conservation flows become more complicated, right? They become longer and longer. But hodograph equations, this explicit solution, it stays the same, right? So when you write hodograph equations, everything simplifies and you get this. All right, so I'm not presenting explicitly conservation laws and commuting flows. They can be found in our paper with Maxime Pavlov.
This argument means that the equation you can transform the equation at the top into like a diagonal system for eta with characteristic speeds psi I, and then decoupled completely from the equation that determines R. I suppose like this is the hodograph equation for the system?
Yeah, in some sense, theta split, but I don't know how to do it at the level of the system. I can do it at the level of solution, but possibly you have a kind of, I don't know, maybe reciprocal transformation. I don't know. Yeah, I don't know. Okay, now I come to Hamiltonian formulation, the second part of my talk. So first of all, for n equals 1, where you have one delta function, u1 delta of eta minus eta 1, the simplest possible ansatz. Then this reduced system is automatically Hamiltonian. This two-phase interaction kernel doesn't enter the system, right? And the Hamiltonian is given by this explicit formula where the function zeta is antiderivative of psi. Psi is a free soliton, right? So it's always Hamiltonian. In fact, this system for n equals 1, the system possesses infinitely many local Hamiltonian structures. It's just one of them, the simplest. All right. For n equals 2 and interaction kernel G given by this formula, all delta functional reductions are bi-Hamiltonian. They possess two local Hamiltonian structures, right? But for n greater than or equal to 3, only one of these two structures survives. So for general n, you have one local Hamiltonian structures. But there are non-local structures as well. So in fact, Thibault will speak about Hamiltonian structure of the full kinetic equation. And they do not have this restriction for the kernel. This means that if you reduce your Hamiltonian structure to cold gas ansatz, right? You should get something non-local in general. Because for local structures require this, right? And it would be nice to do this, to see what you get if you reduce it to cold gas ansatz. All right, but there is one case which possesses infinitely many local Hamiltonian structures for any n, in particular hard-rod case, in general separable case, or hard-rod case, where this interaction kernel is a constant, -8, right? Then you have infinitely many local Hamiltonian structures. And usually such things happen when the system is linearizable. And indeed, hard-rod reductions for cold gas reductions in the hard-rod case is a linearizable system. And in fact, the full hard-rod kinetic equation is linearizable. And I will say a few words. Okay, now what is what are Hamiltonian systems of hydrodynamic type? So suppose we have a system of this form. So in indices, it's this: RIT equals VIJ RJX, right? So R is a column vector, R1, Rn, and V is an n by n matrix. Stop working. V is an n by n matrix. Okay. So we say that the system is Hamiltonian if it can be represented in this form, a certain differential operator acting on variational derivative of a functional, where in fact this functional is of hydrodynamic type, so it only depends on R's but not their derivatives. And the Hamiltonian operator is of Dubrovin-Novikov type. So it has this form. In this form, Gij is interpreted as a metric. Gammas are interpreted as Levi-Civita-Christoffel symbols, and the metric must be flat, right? So an expression of this form defines a Hamiltonian operator, so it's Q-symmetric, satisfies Jacobi identity. If and only Gij is a flat metric and gamma ijk is the Levi-Civita connection of this metric. Right? So now, what are the conditions for the matrix V such that it possesses this formulation? The system possesses Hamiltonian formulation. These are so-called Tsarev's conditions. You get this pair of equations. So for this equation is algebraic, GIS, VJS, GJS, VIS, summation of S, all right, just algebraic conditions, and also differential conditions. So given a matrix V, first you try to solve these Tsarev's conditions and recover and say everything you can about the metric using these Tsarev's conditions. And then you impose flatness of the metric. This is how you look for Hamiltonian structure. And this is what we did with Pierre-André. So remarkably, for this cold gas reduction, Tsarev's conditions can be explicitly solved. In fact, everything that is related to kinetic equation for soliton gas can be explicitly solved somehow, like almost in quadratures. So let me show you. Here I copied the system for soliton gas. The matrix capital V consists of n Jordan blocks of size 2 by 2. And the first set of Tsarev's conditions implies that G, the metric, also consists of 2 by 2 Jordan blocks, but this time of Hankel type, 2 minutes. Yep. Hankel type. It turns out that the other set of Tsarev's conditions specifies this function's unit in this form, right? So ni's, these ni's are given by this formula, mi's are given by this formula, and here s's are arbitrary functions, and gi are also arbitrary functions. This follows from the first set of Tsarev's conditions. And then you require that this metric given by this formula is flat, has zero curvature tensor. And this gives you the special form of the of epsilon. By the way, so for the hard road case, I will come to the hard road case later. You see, this formula is the same, but derivatives of epsilon of the interaction kernel are zero. So mi's are just this given by this one for the hard road case. So let me show you the KdV case, averaged, soliton gas for KdV. So the Hamiltonian, so in this case, the functions si's are just eta i's. The functions gi's. So remember, I have these arbitrary functions of one variable and arbitrary functions of two variables, right? So for KdV, and here you have to substitute the corresponding to soliton kernel, right? So for KdV, you get si's are just eta i's, gi's minus 2i, and this choice is unique. Right, only for this choice, the metric is flat. So I have only one local Hamiltonian structure. Hamiltonian density is this, density of momentum is this, and Casimirs are a bit more tricky. So here I take the case n equals 2, where when we have two Jordan blocks, when we have the system of this type, two Jordan blocks only, then two Casimirs are easy, are simple, and then generalized to arbitrary n. But the other two Casimirs are quite tricky, and they're expressed in terms of the log function, the logarithm function. So this was unexpected for us. But then Gena told me that they came across the logarithm function in some other context, and maybe this is not accidental that we have the logarithms, right? Then hard road case. In the hard road case, S of eta is just eta. The two soliton kernel is this, and the kinetic equation takes this form. The delta functional reductions are Hamiltonian, and the coefficients ni and mi are given by this formula, where s's are arbitrary functions, and g's are given by this explicit formula, where CI's are extra and arbitrary constants. So in this case, in the hard rod case, we have infinitely many local Hamiltonian structures which are parameterized by n arbitrary functions and n arbitrary constants. And this suggests that hard rod case is actually linearizable. And in fact, not just hard rod cold gas reductions are linearizable. The full kinetic equation is linearizable, but I don't have time. I stop here.
That's very short, because in derivation, the can't run its theories on it.
Not really, not really. In fact, I'm forgetting the number. There was an American physicist, right, who did this long ago. I forgot the surname. Yeah, it's
My question, I think.
Yes.
So, in the kinetic equation plasma, people tried a lot of such things. I mean, particularly, I mean, lots of Poisson equation. And the trouble with such reductions, they are there is almost string stability. I mean, it was study such.
no, this wasn't.
It wasn't now.
Jordan, it's not hyperbolic, it's parabolic.
Well, okay,
In a sense, yeah.
I mean, with the original reductions, without this addition, durable bond.
Yeah. No, this is, of course, yeah.
But the eigenvalue are the
Mhm.
in what the limits there. One more quick question.
Just what do you mean by linearizable?
Can I show a few more slides?
Once, two.
So, and you introduce the moments, right? Then you write your kinetic equation in this form, right? The full kinetic equation reduces to just one equation where A0 is integral f d-eta and A1 is integral eta f d-eta, right? Okay, or in terms of the moments, you get this. Now, what is second slide linearizability? All right, so what do? You introduce a new independent variable y. Instead of tx, you pass to ty, where dy is this. It's called the reciprocal transformation. Right?
This is my x hat.
Yeah,
Okay.
and then you introduce AIs, rescaled AIs. And then your hydrodynamic chain becomes linear, and the kinetic equation becomes this.
So this must be related to what I said at the end, but what we had is a general thing for not just for hydrogen, linearized, but it's similar to situation.
For general soliton gas.
Yeah.
Yeah.
But
it's slightly different. We don't have the DT part.
yeah, but that's the evolution.
So that's the evolution.
Yeah. But I mean, maybe if it fails to satisfy some of the conditions you need, but you can, there's a mapping of independent coordinates that make it linear.
Okay, I think that's for further discussion. Thank you, Jim, again.